Hello everyone, and thank you for attending today's webinar, How to Correlate Micro-XRF and SEM-EDS for Optimal X-ray Characterization of Materials. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application engagement tools you can use. All the engagement tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A engagement tool. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, it will be answered later via email. Please know that we do capture all your questions. A copy of today's slide deck and additional help materials are available in the Related Content tool. We encourage you to download any resources or links that you may find useful. For the best viewing experience, we encourage using a high-speed and stable internet connection and closing any programs or browser sessions running in the background that could cause issues. Strong Wi-Fi connections are acceptable if they are stable. Unstable Wi-Fi due to congestion or other causes can result in connectivity drops. Webinars are bandwidth intensive, so closing any unnecessary browser tabs will help conserve your bandwidth. The webcast is being streamed through your computer, so there is no dial-in number. For the best audio quality, please make sure your computer speakers or headset are turned on and the volume is up so you can hear the presenters. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If the slides are behind, push F5 on your keyboard to refresh the page. You can find additional answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce today's presenter, Dr. Shangsheng Mu. Shangsheng joined EDAX in 2018 as an applications engineer. Working out of the Pleasanton, California office, he's responsible for providing technical expertise, conducting demos, teaching training courses, and after-sales support. Shangsheng also performs testing and validation for the engineering department and provides support for the marketing team. Prior to EDAX, Shangsheng was the lab manager at the Southeastern North Carolina Regional Microanalytical and Imaging Consortium in Fayetteville, North Carolina. Shangsheng graduated from Chengdu University of Technology with a Bachelor of Science in Materials Science and Engineering. He earned a Master of Science in Materials Science and Engineering from New Jersey Institute of Technology. Shangsheng completed his PhD in Earth Sciences at Boston University. Now over to Shangsheng.
Thank you, Johnson, for the introduction. Good morning, good afternoon, good evening, everybody. Thank you for joining this webinar on Micro-XRF and SEM correlation. So in this webinar, first, I'm going to give you a brief introduction to the benchtop Micro-XRF and SEM-EDS. Then I'm going to show you differences in data from SEM-EDS and Micro-XRF. The goal is to discuss any advantages and disadvantages to either technique and to observe how the data complements the other technique. So for SEM-EDS and Micro-XRF, both techniques detect X-rays generated after interaction with the sample. In the SEM-EDS, the electron beam interacts with the sample surface to generate X-rays, and those X-rays are captured by the EDS detector mounted on the side at an angle. And for the benchtop Micro-XRF system, we have an X-ray tube to generate X-rays, and those X-rays are focused through the X-ray optic to interact with the sample. and the fluorescent X-rays emitted from the sample are captured by the X-ray detector mounted on the side. I have to mention that there are different setups, like the X-ray optic geometries for benchtop Micro-XRF. In this case, I'm showing you that the X-ray optic is with a vertical beam geometry. So for this geometry, the X-ray is straight down, perpendicular to the sample. In this case, it can eliminate any shadowing caused by the sample topography. And also the X-ray beam has the same dimensions in both X and Y directions. And you may see some other X-ray optic geometry, like the X-ray optic is mounted on the side, just like the X-ray detector. So to summarize, in the SEM-EDS, the X-rays are generated by electrons, and in Micro-XRF, the X-rays are generated by the X-ray photons from the X-ray tube. For both techniques, they are possible to do qualitative and quantitative analysis, as well as mapping and line scan. And both of them use SDD detectors to detect X-rays. So the SDD detector is a liquid nitrogen-free operation, and it's capable of processing high count rates. For Micro-XRF, this is a non-destructive technique. There is no beam damage, and coating is not required, so you can analyze a non-conductive sample as is, and there is no heating of sample because there is no electron beam sample interaction. Micro-XRF requires minimal sample preparation. Mounting and polishing are not required, and conductivity is not an issue. Sample shape and height can be irregular, and this technique is flexible with how the sample is loaded. So thicker samples can be bulk samples or can be loaded directly on the stage. For thinner samples like particles, powders, fibers, they can be mounted. So the detection limits for Micro-XRF, this is 10 times or better for higher Z elements compared to EDS. It uses higher energy X-rays to generate lines not detectable with EDS, such as strontium, zirconium K, silver K lines. So those lines are useful when lower energy lines have overlap. This is usually the case with EDS spectrum, because EDS cannot generate L and K lines for those higher Z elements. It can be operated in low vacuum or air mode, so this allows analysis for liquids and any sample that will dehydrate or degas in the vacuum condition. It may also have the helium flush option. This allows vacuum performance at atmospheric pressure, because the X-ray attenuation in helium gas is very low. Micro-XRF generally has larger spot sizes, and the sample chamber and stage size are much larger than the SEM chamber and stage, so this is more appropriate than SEM-EDS for larger scale features. Excuse me. So X-rays are more penetrating than electron beams, so it gives better detection of subsurface composition. So the analysis depth for the Micro-XRF is microns to millimeters. And imaging is integrated with digital cameras. Micro-XRF usually equipped with high magnification and low magnification cameras to guide you analyze the sample and to take sample images. The smallest spot size for micro-XRF is around 20 to 30 micron, and usually they are also equipped with millimeter-sized colorimeters to do analysis on larger areas or to map larger scale samples. I have to mention that there is another approach, so that is called SEM-based micro-XRF. So this approach, it attaches an X-ray source with X-ray optic to the SEM to excite the sample and use the EDS detector mounted on the same SEM to capture the fluorescent X-rays. So basically, the X-ray source and the EDS detector form a micro-XRF analyzer for the SEM. This setup, it can generate high energy X-rays in the SEM, like above 20 kV, but the sample needs to be prepared to put in the SEM chamber under vacuum, like you have to polish and coat your sample. And also for this SEM micro-XRF, the sample size is subject to the limitations of SEM chamber and the stage, so your sample has to be fit into the SEM chamber and can be mounted on the stage. So large samples cannot be accommodated in this SEM micro-XRF system. So my point is, having a separate benchtop micro-XRF, this is a more flexible approach. For SEM-EDS, it has a much better light element, low energy light sensitivity, and it has nanoscale spatial resolution if you have the right settings for the SEM and EDS. So EDS has a weaker penetration of beam, so basically the analysis depth is confined to the near surface area. And due to the limitation of the SEM chamber and stage, it can only analyze relatively small sample. And EDS requires more involved sample preparation. If your sample has topography, you have to cross-section, grind, and polish your sample to produce a flat surface. And if your sample is too large to fit into the SEM chamber, you have to cut your sample. If your sample is non-conductive, you need to coat your sample with a conductive layer. And also your sample has to be mounted on the stage. So typically SEM is vacuum only. Some SEMs have the option to use a low vacuum mode to help you mitigate the charging artifacts on your sample. For SEM-EDS, we use a separate interface for sample imaging, like the SEM images. They are captured by the secondary electron detector or backscatter electron detectors mounted on the SEM column. So moving forward, I'm going to show you 3 categories of application examples. First, I want to show some EDS and micro-XRF app data to highlight the sensitivity to either technique. And then I'm going to show you some large area mapping examples for EDS and micro-XRF. Because EDS has much better spatial resolution than micro-XRF, so I'm not going to discuss mapping on small features. Lastly, I'm going to show you an example of correlative analysis using both EDS and Micro-XRF. This is a This is a spectral overlay for a glass sample using both EDS and Micro-XRF at 20 kV. So red is the EDS spectrum and blue is the XRF spectrum. So they are normalized to the silicon peak in purple. So we can see in the lower energy range, we have very high peaks for carbon, oxygen, sodium in the EDS spectrum. So EDS has much better sensitivity in the low energy range. And as we increase atomic numbers, we start to see chromium, manganese, and iron peaks in the XRF spectrum. And we don't see those trace elements from the EDS spectrum. And we can also see there is a rhodium L line. So this rhodium L line is not from the sample. Actually, this is from the X-ray tube because we use a rhodium X-ray tube to generate X-rays for the Micro-XRF. So for Micro-XRF, you do pick up the tube scatter lines. So whatever anode materials your tube has, you'll get these lines in your spectrum generally. So if you do not filter this out. So in this case, we have the rhodium L line. So this is an artifact peak you see in the spectrum. So this is one thing that you don't have to deal with on the EDS side. This is another example of for a glass standard. So this glass standard is with different elements doped in concentrations in between 300 and 500 ppm. We see the SEM-EDS spectrum in blue outline. It has very nice carbon, oxygen peaks, and also the sodium peaks is much higher than the peak from the XRF spectrum. But as we go to the higher Z side, we see a bunch of the doped trace elements popped up in the XRF spectrum. And we barely see them in the EDS spectrum. So we can see a little bit of chromium, iron, and nickel in the EDS spectrum. But for all the other trace elements, we do not see them at all. So Micro-XRF has much higher sensitivity for the higher Z elements. This is a spectral overlay for a boron sample with different trace elements in the range from 5 to 40 ppm. In the EDS spectrum, in the blue outline, we see the very high boron peak, but we do not see this in the Micro-XRF spectrum. In EDS spectrum, we do not see the peaks starting from calcium, and we can see calcium, chromium, manganese, and the nickel peaks. So those trace element peaks from the Micro-XRF spectrum. So that's the difference in sensitivity between SEM-EDS and the Micro-XRF. This example shows EDS quantification on trace amount of carbon in steel. So the EDS detectors with silicon nitride window and CMOS-based electronics can quantify 0.5 weight% of carbon, even and high count rates. In the spectral overlay, we see the carbon peaks acquired at 20 kV, 15K input count rates, and also 200K input count rates. In the chart on the right-hand side, this is carbon concentration as a function of increasing count rate up to 200K. So we can see as we increase the count rates all the way up to 200,000, and the carbon concentration is pretty accurate and stable. So the mean concentration is 0.497. It's pretty close to the certified number of 0.5, and also the standard deviation is very small. On the Micro-XRF side, current Micro-XRF technique has many limitations on detecting carbon. Basically, carbon detection is not practical in Micro-XRF, and quantification of carbon is not feasible. This example shows EDS sensitivity at extremely low energy range, and this is aluminum tape on silicon carbide. So this was mapped at 2 kV. So we see the EDS detectors with silicon nitride windows. So this has very good X-ray transmission in the extremely low energy range, so it can separate aluminum alloy, which is 73 eV, and the silicon alloy, which is 92 eV. And also we have very strong carbon signal in the map. This example shows, so this is a white gold ring analyzed using Micro-XRF. The top right is the video image of the analyzed area. So we see in this XRF spectrum, it shows silver K line and palladium K lines. So we can use these higher energy lines to generate lines not detectable with EDS. So if you have overlaps in the lower energy range on the EDS side, you can use Micro-XRF to generate the K lines for those higher Z elements to confirm the presence. This is XRF mapping example of a large and non-conductive sample. This is an overlay of a printed circuit board. It shows 5 different elements. So basically, Micro-XRF is more appropriate for mapping larger scale maps with rougher topography in shorter time. Like in this case, for the PCB board, it has many components above the surface, but with Micro-XRF, it can handle this rougher topography without any problem. And also, this PCB board is non-conductive, but in the Micro-XRF, it can be analyzed as delivered quickly and easily. This is another PCB board, 2.4 by 1.8 centimeters, relatively large, non-conductive sample. So we see different energy lines, and some of them are pretty high energies. And I added both gold L lines and M lines, so they are in the bottom left corner. So I added both lines because they have different escape potentials. So you get different information from using both lines. M line is more representative of the surface, whereas the L line comes from a greater depth underneath the surface, which is more representative of the subsurface presence of gold. In this case, the two maps are pretty much the same. This means through the depth of the sample, gold does not change in distribution or area. This example shows even larger sample. So this case, we use Micro-XRF to determine the depth and the path of ion infiltration across the entire pavement core from an exposed roadway surface. So in this montage video image, so this is the concrete pavement sample. The left-hand side is the top surface or the driving surface, and the depth beneath the surface or the length of this sample is 70 millimeters. In the right, we have this overlay of potassium, sulfur, and calcium elemental maps. So within this map, we can clearly see the depth and path of ion infiltration. On the SEM side, we can also do large area EDS mapping by using the montage option. So large area EDS mapping can be accomplished by automatically stitching individual fields of view together. This example, this is a 2.5 by 1.5 centimeter geologic section. It consists of 24 by 27 fields of view. But for this kind of application in EDS, generally the sample preparation is required. In this case, we need to polish the section, and also we have to coat the section to make it conductive to be analyzed in EDS. This montage EDS mapping, this example is sand grains mounted in epoxy, and the collection time was 20 minutes. It consists of 8 by 7 fields of view. So we can see that because EDS has much better spatial resolution, so those EDS montage maps provide much higher spatial resolution to interpret concentration variation within sand grains. And also with EDA's large area, light element mapping is possible. So here we can show the oxygen map distribution. This example is correlated analysis on solder sample using both SEM-EDS and the Micro-XRF. The EDS analysis was done at 20 kV for Micro-XRF. We used 45 kV and 30 micron polycapillary optic. So we analyzed the spots circled in orange using EDS. And in the EDS spectrum, we have gold and bismuth suspected in the low energy range, which is circled with orange. So we put the sample in Micro-XRF and found the same spot and analyzed this spot. So we used aluminum and rhodium filters to increase the peak to background ratio. So in the Micro-XRF spectra, we are able to see the gold L line, bismuth L line, silver K line, and tin K line. So those lines were unseen with EDS. This is another spot analyzed with Micro-XRF. We used aluminum filter to show significant bromine and strontium peaks, which were unseen with EDS. And we can also detect tin K and barium K to confirm the presence, whereas EDS must use the L lines only. In this case, we used high magnification SEM. So at this high magnification, EDS allows more precise beam location. So we are able to analyze the 3 very small features using EDS. And we can figure out from the EDS spectra that those 3 different features have different compositions. So EDS is good for analysis of fine features. With Micro-XRF, the spot size would be too big to resolve those 3 fine features. In summary, Micro-XRF has improved detection limits for higher Z elements, even more so with beam filters. This allows operators to go back to EDS and find trace elements missed the first time. Micro-XRF requires minimal sample preparation, so the analysis it can analyze as delivered samples quickly and easily in a low vacuum and air mode. So this would be suitable for samples that cannot be exposed to a vacuum, like those samples will dehydrate or degas in a vacuum. Because Micro-XRF has larger sample chamber, large stage, and a larger spot size, it's more appropriate than SEM-EDS for analyzing and mapping larger scale samples with rougher topography. Also, analysis depth is greater than SEM-EDS because X-ray beam is more penetrating. For SEM-EDS, this is more appropriate for smaller scale features and more precise locations because SEM-EDS has much better spatial resolution, and it has improved detection limits for light elements. So if the detectors are equipped with silicon nitride window, which has super low X-ray transmission, this allows separation of extremely low energy lines like silicon L line and aluminum L lines, and also it can do a trace amount of carbon quantification and high count rate. The montage mapping option for EDS allows an analysis of relatively large samples with light elements. So in conclusion, in an ideal world, every lab would have both tools to accomplish the full needs of spectral analysis. Like we can use Micro-XRF to give us high sensitivity for higher Z elements, and on the low energy light element side, we can use EDS to do your job. All right, so before we ramp it up, I'm going to answer a few questions. Okay, here's one question. Why does a given filter allow better detection of some peaks with Micro-XRF. Okay, so beam filters, they absorb X-rays and certain energy ranges. So it eliminates high background and tube scatter lines to improve the peak to background ratio. So each filter applies to a certain range. And there are some common beam filters like aluminum, titanium, nickel, niobium. So each of them applies to a certain energy range. Next question, will the X-ray source be possible to change with different source for different energy? Yes, it is possible. You can use different X-ray tube materials and to operate the instrument at different energies. Next question is, can Micro-XRF measure multi-layer coating thickness? Yes, it is. We have coating layer measurement software. So with this, you can measure the coating thickness for multiple layers. For a semiconductor sample, you can use this to figure out the layer thickness for different layers. And also it applies to other applications. Next question, does the SEM magnification change the spot size in EDS? It does not. The spot size in EDS or the interaction volume of the EDS, this is determined by the accelerating voltage. Next question is, what are the total measuring time for a montage with EDS? So the answer is, it depends. It depends on the collection parameters you use. Like for the first montage I showed in this presentation, which is the entire geologic section, I used more than 20 hours to collect that montage map because I used sort of higher quality to collect the sample. Like I used a longer dwell time. And for the second montage example, which is the sand grains, I used just 20 minutes to collect that map. Next question is, does Micro-XRF detect ppm level elements? Yes, it does. Micro-XRF can do single-digit ppm level analysis. Next question is why the perpendicular incidence of exciting beam avoids shadowing. So that's because the X-ray beam is straight down. So if your sample has high topography, it will not be affected. But if the X-ray beam is at an angle and your sample has high topography, the X-ray beam will be shadowed by the high topography of your sample. Next question is, what's the typical energy of the X-ray using here? So for the Micro-XRF examples, we used 45 kV. And for the EDS analysis, I think most of them were 20 kV. Next question is, what's the difference between bulk XRF and micro-XRF? So bulk XRF also uses X-ray tube to generate source. It has larger X-ray beam diameters. Usually they are millimeters or above. So they have a large analysis depth and area. The sensitivity improves with increasing Z, but there's no stage scanning option. So the micro-XRF, it utilizes the benefits of conventional XRF while implementing the micro-spot X-rays with a movable stage. Like in the micro-XRF, the smallest spot size can be around 20 to 30 micron. Next question is why EDS is more sensitive in the low energy range. So there are a couple of reasons. EDS excitation comes from electron sample interaction within the sample itself. Therefore, the process is efficient and creating low energy X-rays above the absorption edges of low energy elements such as carbon, oxygen, nitrogen, and so on. Another reason is the EDS detector uses a silicon nitride window to improve the X-ray transmissivity in the low energy range. On the micro-XRF side, the excitation of lower energies is not as efficient because there is very little X-ray excitation emitted at low energies. The excitation X-ray tube generally has a heavy beryllium window to maintain vacuum in the X-ray tube. The detector for micro-XRF generally has a beryllium window as well to block the light in the sample chamber. The beryllium has lower or much lower X-ray transmissivity in the low energy range. Also, for micro-XRF, the excitation efficiency is better and higher energies due to the more efficient excitation emission of the X-ray tube at the higher energies. Next question is, what are the maximum kVs for EDS and micro-XRF? The typical maximum kVs for SEM-EDS is 30 kV, and for micro-XRF, it is 50 kV. Next question is, where does the background in micro-XRF spectrum come from? So similar to EDS, in micro-XRF, we do have a background in the spectrum. For EDS, EDS is The EDS background is generated by the electrons being accelerated or decelerated in the sample, while Micro-XRF does not have electron-sample interaction. The interaction of electrons and anode materials in the X-ray tube does generate a bremsstrahlung background, and it will show up in the sample spectrum. So as well as tube X-ray lights. So those are the artifacts. Like if you use a rhodium tube, you will see the rhodium L lights at around 2.7 keV and the rhodium K line at around 20 keV. All right, I think it's time to ramp up. Thank you for all the questions you shared today and all of the questions, the unanswered questions. I will follow up on them and email the answers back to you. Thank you everyone for your attention and time. Bye.